Okay, let's do day 6 now. Some sort of optimization problem, I believe. Okay. See if we've done this correctly. I've gotten pretty good at using these ranges recently. So that should get us the times. Okay, we can do the same thing for distances. Okay. So, let's see how much we can accelerate by 1 millimeter per second. And you can't move while you're accelerating. And it's only optimal to accelerate at the beginning if you... Yeah, okay, so that's true. So this is a game of finding out how long you want to accelerate before going as far as possible. So in this case, if you accelerate to a speed of 6, you can go to a distance of 12 or 10 perhaps let's see. Yeah, okay. Hold for 5, move for 10. So there's a point where our milliseconds, or okay, millimeters passed goes up, peaks, and then it goes down. And let's see if it's symmetric. It is, okay. Haven't thought about this enough to make sure that's a math property, but maybe it is. So the game is to find out, perhaps using binary search, how many ways, okay, wait, how many speeds are bigger than that. So that's not that many, right? Maybe it is. Ooh, fancy. Okay. So, let's see. This is for each test case, essentially. Call it race. Okay. So we're going to push in all of the, every time we find a higher score, that's what we'll push in. Okay. Let me think about this for a sec. Okay. So our score is going to be the speed we're at multiplied by how long we can move for. And if that score is greater than the distance, shouldn't call this score, but whatever, then that means we have a higher score. Wait, what? Ah, I see. That means we've won, and at the end of this, this might time out for a longer case. I don't think we need to actually do that type of math here. Let's see. This may time out. Doesn't. Good. Okay. What is kerning? Oh, it's okay. Yep. What? Okay, wait. what if we did join those together, and that becomes a string? I think that's what they're saying, is that this whole thing is actually a single time and a distance. Except, well, I still want this to be a number, so gonna do something strange like that. So now I believe this will probably time out. I don't think there's going to be an obvious way to do this. Yeah, because that's like, that would be a loop of 70,000. Well, even if it times out, let's just make sure I'm still thinking of this correctly. How many ways are there to beat the record in this much longer race? Oh, wait, we want to concatenate all of these. Okay. Oh, that's a huge number. There's no, yeah, that's not even gonna run. Well, let's see if it does it for the small case at all. Yeah. Okay, so we're still correct. We just need to find the faster version of this. 7-1. Okay. So let's see. Optimizations. Well, let's see how big this number is. I don't even know if I can store that in C++. Actually, yeah, I think that fits. Just barely. Whoops, wrong place. Okay, so let's think. There's gonna, ooh. Oh wait, wait. Okay, so the number fits. That's good. So that is so big now. I need to think of some sort of math now. Okay. So we know probably that, well, let's just look at the scores we're getting. I think this is symmetric, that once we know half, we know the whole thing. Well, actually, that's not super helpful. But, oh, okay, because this is the really big number version. Well, we can actually use this. Yeah, the ends are symmetric. Okay, so somewhere in the middle. If it's symmetric, what does that tell us? There is a point where halfway through, if we start losing. I think this is a binary search problem. Yeah, it's symmetric. Okay. Well, except for the 0, but it's symmetric otherwise. Okay. let's think. So how do we find what the score we need to beat is? Okay, so we know it's going to be this huge number. And what we want to find out is how many scores beat that. So let's see. We know that there's a point that we can reach where the more time we add, we start to lose out in score. Perhaps this is a lower and upper bound problem. Because in the cases of the individual cases, like for 15 and 40, the upper bound is like here and the lower bound is there. And perhaps if we know how many numbers are in between these upper and lower bounds, we are able to do this. We're able to find out the first number which satisfies this condition. So how do we know how big the gap is? Well, we need to know what number we are at this point to calculate this. We know that this is at least time of 15. That's 0, 1, 2, 3, 4. That's 11. So because we were waiting for 4 seconds, we moved for 11. 11 times 4 is 44. So I think we have enough information to do binary search on this. Not totally sure yet on how to do that, but I think we can do that. So let's think, how can I turn this problem into binary search? Let's have a lower and upper bound, and for convenience sake, I'm gonna introduce a little shorthand for big numbers. Okay, I'm more confident this is binary search now, so I just need to find out where this and that is for any given number, or I guess the one number we have now. So in a sense, I could probably even do that manually, but that's not interesting. Well, lower starts at 0, upper starts at the highest end of time, which is 15. So, or sorry, 15 in this case. In our case, it's going to be all of these mixed together. Let's do the small one first, so it's going to be 71,030. So, so that's going to get us the middle of our binary search range. If it's above the distance, then we need to update. What's going on here? Is that an actual error? It's not, I think. Okay. Oh. Well, it's just going to loop forever, so. Okay, so if we're still above, if we're above, that's good. Oh, does binary search work on a range like I think it does? Well, I guess we could cut the search space in half. We could just, however many numbers we find that are larger in the first half, we could just double that. So as soon as we get to that, then we can stop. So how do we know when we're there? Perhaps we could check one ahead, maybe, and just say that if it's less than the last one, you know, that's the new upper bound. That's sort of a cheat, but that avoids this problem. Yeah. Maybe what I should do is see if I can find the point where this starts to happen. So I should find, I think the upper bound, what's easier to find? Let's think. I think the lower bound should be easier to find. So let's think if we can at least do that. That's step one. Okay. So if we're below the distance, below or equal to, the lower bound has to be at least the number. Let's print the lower bound we're getting for now. See if we can converge onto that. Nothing happens. Just toss that out for now. Okay. Oh, whoops. We never updated the upper bound. What am I doing? Okay. Just worried about this, doing it like this. This doesn't seem, there's almost certainly going to be problems with doing that. For example, what if the number okay. Okay, so we went all the way up to the upper bound. That doesn't seem... Well, actually, wait. Yeah, this one's easy. I just can't think about this right now. Let's say for 10 steps we move at 7, 1, 5, 20. It's not enough, so let's say for let's say for 20 steps we move at 7, 1, 5, 10. That is enough. So I'm just trying to find out the exact point where we can stop moving. Well, in that case, you know what? Maybe I should just do it by I mean, it's kind of lame if I did that, right? So actually, the numbers are so big, it's honestly kind of hard to see what's going on. let's say that for 73. Right, and that's only 2 billion. This thing is not 2 billion, it's much bigger. 100,000 million billion trillion. Okay. I don't know though. It is possible to just like oh, I need to take off like 1,000. Let's take off 1,000. If we do like 386 76673 for 1,000 steps. This gets us to 38 billion. Okay, so we need to take off another like 2 digits, right? So I think, yeah, that's essentially what I want to do is find the upper bound and then find the lower bound. Okay. So for my other one, my upper bound was not cutting it. Oh, wait. That implies there's only like 2 answers, which is not correct. Wait, why doesn't that end? Sorry. Yeah, I should be able to do binary search easily by now. I just haven't thought about it apparently enough. And I'm not convinced this is truly how the problem is supposed to work. Okay. So let's see. Seven, 5, 30 minus 13 times, yeah, times 71517. Oh, whoops, wait. Yeah, there we go. Okay. So that's the lower bound. So 14, I think, is what we're really looking for. So if we do 71530 minus 14 times 14. Oh, I can't use this calculator, dude. Yes, times 14. What is going on? Oh, wait, yeah, that's right. So that's the first instance where we beat that. So for some reason, our upper bound is actually what we want. That is the lower bound. So, So we have that. You know, very interesting. Oh, this is easy. I haven't thought about binary search in a while. Okay. Dang. Yeah, I think a lot of people, yeah. Oh. Yeah, I wasn't even that fast for the first one either. Okay. Well, slow and steady eventually will win the race. Oh wait, if I have the lower bound, we know it's symmetric, so we know that that's how many numbers that don't fit, if that makes sense. So, wait, let me say it like this. If we know the lower bound, that's how many numbers we can cut out on the lower side. So I think we can cut out that many numbers on the upper side as well. So, really, our total is going to be how much time there is minus well, actually, wait. Can't get rid of some stuff. But does that make sense? I think it does, actually. Like, that is the correct answer there. You know what? It might be one off somehow. Like, it's just somehow it's gonna be one off. There are a couple of reasons that could happen. Alright, you know what? That symmetric factor, I did not think it would come into play so quickly. So I had this solved the whole time. I just didn't think. Okay, that was easy. You know what? Easiest problem in a long time. Nice. Okay. I feel good about this. See you tomorrow. Oh, wait. Let's see our rank. The rank is bad. I could have solved this much faster, but yes, that's not very good. But oh well. Yeah, that was a good refresher in binary search though, so I'm actually happy about that. I think I'm not. Yeah. Okay. Well, yeah, he beat me on that one. All right. Next time. Actually, there's one final point to make. I was doing some time testing. It turns out the brute force solution actually runs in about 0.1 seconds. Yeah, 0.14. So I just did brute force incorrectly. I was using the small integer type instead of the big number type, which wasn't getting me the right answer. Or I think it kept looping. I don't know for sure. Something strange happened. So I didn't have to do any of this. This is all a waste of time. But I mean, this is also, I mean, it's a good test. People should know binary search. And this is way faster. This goes at 5 milliseconds, 2 milliseconds, right? So that's, I don't know, 50 times faster. Was it worth it? Not really. But it's good to have both.